moment of area. Okay, and this is our radius of gyration. Okay, so that is what we have. So then the next thing we are going to do is we are going to determine our I-axis. Okay, we have to determine our I-axis. So I'm going to take this image over here. Okay. Right. So I want you all to focus on the cross section. Okay. So I want to focus on the cross section. So the first thing we are going to do is we're going to determine I-axis. So this is equal to width, okay, width depth cube over 12 plus by width multiplied by depth multiplied by our distance y bar minus small y squared. Okay. So there are a few ways that we can do that. Okay, but more important, we know the axis of interest is our x-axis, right? Like what I taught you before, if that is the axis of interest over here, the parallel is known as our width, and the perpendicular, right, to the axis, this is known as the depth. Get this figured out really quickly. It will reduce a lot of problems. Okay. So what I'm going to do is I'm going to take this. So I'm going to do I-axis. Okay. So I'm going. My strategy is this. Okay. I'm going to take the second moment of area of the big box. Okay. So this is our axis. And this over here, okay, I'm going to take it as a solid. And the geometry over here, from here to here, that is 120 millimeters. And then this will be equal to 100 millimeters. Okay. Then I'm going to subtract. I'm going to take away the two pieces at the top and the piece at the bottom. Okay. And these dimensions are going to be, the distance from here to here is 100. And the distance from here to here is what? So the thickness is 10. So 90. So it's 90 divided by 2 is equal to 45 millimeters. Okay, so I'm going to calculate the second moment of the solid first. Then I'm going to take away the top and the bottom. Okay, and that is your second moment of area. So over here, the width is equal to 100. The depth, okay, and then this is minus. So it happened to be the centroid of the two small is also at the center, right? So when it's at the center, this term is equal to 0. Okay. Now I will do another method. Okay. To calculate the same the same second moment of area, but we're going to use a different method. Okay. And the answer will be the same, but is slightly more lengthy, but it's okay to be lengthy. Okay. So the width is now 45. The depth is 100 power 3. Okay. Again, divided by 12. So this will be equal to, if I can find my calculator. So 120 power 3, that's a 100 divided by 12. So it's equal to 14.4 times 10 to the power 6 minus by 45 times 100 power 3 divided by 12 times 2 is 7.5 times 10 to the power 6. So this is equal to 14.4 minus 7.5 is equal to 6.9 times 10 to the power 6 millimeter 4, or 6.9 times 10 to the power minus 6 meter 4. So we have our second moment of area. Now, with this, let's do a different method. Okay, if you're not very sure, we can do a different method, and the answer should be the same. Okay, but the formula slightly changes, and I'll show you why. Okay, so the second method is again the axis of interest is here, right? And then we know for the fact that this is always our width, and this is our depth. So I'm going to call the center part, I'm going to divide this into 3 parts. Okay, this is number 1, this is number 2, and this is number 3. Okay, so I divide them into 3 different parts. So IXX1, so the width is 10, the depth is 100. Okay, plus now this happened to be 0, or yeah, it's exactly, or if you call it if you call this, so 100 divided by 2 minus by 100 divided by 2, this whole thing squared, right? So this term is as good as equal to 0. Okay, for I-axis for the first part, because the global centroid and section 1 centroid are exactly at the same position. Okay, so 100 power 3 times 10 divided by 12 is equal to 8.833. Okay, 0.333 times 10 to the power 3 millimeter power 4. Let me do it. 100 power 3 times 10 divided by 12, 833.333. Okay, so that's our width is 10, our depth is 100. Correct. Then we are going to determine IXX. Of 2, which is also equal to IXX of 0.3, right? So the width is equal to 100. Our depth is 10 cubed power of 12. And then we have an area now, plus by 100 times 10. And then we have this term over here. So the global centroid from the datum, okay, so this is where my datum is. Okay, so this is what we call datum, right? So that distance, right, to XX, right? So this distance from here to here is equal to what? It's equal to 50 plus 10, right? So it's 60. And then minus the individual centroid, right? So the individual centroid, if I zoom in, is exactly at the center down here. Okay, it's exactly at the center down here. Oh, right, it's exactly the center down here. And that value relative to the datum is 10 divided by 2. And then the whole thing squared. Okay. So this will be equal to 60 minus 5 squared times by 100 times 10. Okay. Plus by 100 times 10 power 3 divided by 12 is equal to 3.033 times 10 to the power 6 millimeter to the power 4. Let me do it again. 60 minus 5 squared times 100 times 10 plus by 100 times 10 to the power 3 divided by 12, 3033. Okay, so therefore Ixx for the whole thing will be equal to Ixx1 plus by Ixx2, okay, and then plus by Ixx3, knowing that Ixx2 and 3 are the same, so it's 3.333 times 10 to the power 3 plus by twice 3.033 times 10 to the power 6. Okay. So this will be equal to 2 times by 3.033 power 6 plus by 833.333 power 3 is equal to 6.899. Okay, 6.899 times 10 to the power 6 millimeter 4, or 6.899 times 10 to the power minus 6 meter 4. Okay. So this value over here, this way of acquiring it, and this way of acquiring it, right? The numbers is the same. This is round off, okay? Right. So either way is fine. So you see how the formula works, okay? So after we get this, we are going to determine the radius of gyration. So let's see what we have, okay? So to apply the formula, we need I, right? So is this a, yeah. So we need I, we have. L L is quick. The next thing we have to determine is our R. Okay, we have to determine our R. So after knowing Ixx, right? So we know that Ixx is equal to A Rx squared. Okay, so Rx is equal to square root of Ixx divided by area. Okay, so we have to determine the area is equal to, so I can take the whole dimension, which is equal to 100 multiplied by 120 minus by twice of what, 100 or 45 multiplied by 100. Okay, so I'm doing the subtraction. Okay, so 100 times by 120 minus 2 times by 45 times 100, so it's equal to 3000, or 3 times 10 to the power 3 millimeter squared, or 3 times 10 to the power minus 3 meter squared. Okay, so that is our area, our cross-sectional area. So from here, we can now immediately determine our Rx. Okay, so we can determine our Rx. Let's go to the square root of 6.9 times 10 to the power minus 6 divided by 3 times 10 to the power minus 3. So the radius of gyration is equal to, I get 47.958 times 10 to the power minus 3. Right. So we have calculated our